Welcome all to the second class of 1175, Introduction to Deep Learning. In the last class, we saw a bit of what neural networks are. Today, we'll continue with the theme. We'll see what a neural network can represent. A quick recap, as we saw in the last class, a great many AI tasks that were previously considered to be solely in the domain of human expertise, have now been successfully taken over by artificial neural networks. These tasks include tasks like voice recognition, machine translation, even tasks like captioning images or playing intelligence games like AlphaGo, or analyzing video, and even mimicry. So what are these amazing neural networks that perform all of these tasks? In each case, the neural network is a function that takes in an input and produces some output. So it might take in a voice signal and produce a transcription. It might take in an image and produce a text caption. It might take in a game state and predict the next game move. So the network itself is a function that performs this transformation. But what's in this function? If a human were to perform these tasks, these functions would be computed by the human brain. And so neural networks mimic the network structure in the human brain. We also saw that the brain in turn is a giant network of neurons, where neurons themselves are these little units that fire when the combined input exceeds some threshold. And so artificial neural networks too are networks of computational models of neurons. And these computational models of neurons are what we will call perceptrons. A perceptron is this unit that receives many inputs. Associated with each input is a weight. The perceptron computes a weighted sum of all of the inputs, and if that weighted sum exceeds a threshold, it fires, otherwise it doesn't fire. So in mathematical terms, if summation wi xi is greater than or equal to the threshold t, the output of the perceptron is 1, otherwise it's 0. Electrical engineers will recognize this perceptron as a threshold gate, and it implements threshold logic. Please remember this term. We'll see it again. Now, here is a different way of visualizing the perceptron. We first compute an affine combination of the inputs. What do we mean by an affine combination of the inputs? What's the difference between a linear combination and an affine combination? So if you have a collection of inputs, x1 through xn, then a weighted sum of the inputs, the summation wi xi, this is linear. On the other hand, if you have a weighted sum of the inputs plus a bias, then this is affine. Now, if you want to have a different way of visualizing it, if I take this linear combination and say summation wi xi equals 0, so if I set the linear combination to 0, then this represents the equation for a hyperplane. In 2 dimensions, it would be a line where the hyperplane itself goes through the origin. On the other hand, if I choose this affine combination and I set the affine combination to be equal to 0, this represents the equation for also a hyperplane, but now the hyperplane could intersect the axes anyway. So the difference between linear and affine is just this bias term. A linear combination is a special case of an affine combination, but an affine combination is not necessarily a linear combination. And so the perceptron first computes an affine combination of inputs. And specifically in the specific case where the bias term itself is minus t, this is going to be the same computation that the earlier model of the perceptron we just saw in the previous slide computes. And this affine combination is then put through a threshold activation. And the threshold activation has the property that the output is 1 when the input is greater than or equal to 0 and 0 otherwise. Once you state the perceptron in this way, then you can also come up with a soft version of the perceptron. The soft version of the perceptron uses a squashing function, a function which takes the input and squashes its value to lie between two boundaries. So a typical one is a sigmoid activation, where the sigmoid is simply a smooth version of the threshold and is a continuous value between 0 and 1. As we'll see in a couple of lectures, there's a lot of benefit to replacing the threshold activations by these soft activations. But then once you restate the perceptron in this manner, as taking an affine combination of inputs and passing it through an activation, which could be anything. So we can also have other activation functions. Once we realize that we can have, we can think of this as an affine combination plus an activation, you can have other activation functions like a tanh, which is simply a scaled and shifted version of the sigmoid. And the activation function doesn't even have to be a squashing function, which squashes the vertical axis. For example, you can have the rectification function, which simply truncates negative values. Or you can have the smooth version of the rectification function, which is the soft plus shown by the blue line. But for now, we're going to continue to assume the threshold activation, as it's easier to develop intuitions with threshold activations. Now, a multi-layer perceptron, or an MLP, is a network of such perceptrons, where perceptrons receive inputs from other perceptrons and may pass on their outputs to yet other perceptrons. We'll see a formal definition of what a layer is later, but basically in an MLP, these perceptrons are organized in layers which are connected to one another. And when these networks have many, many such layers, they are said to be deep networks. So what is this term deep? What does it mean for a network to be deep? What is the formal notion of depth in this context? For this, it turns out there's actually a very formal definition of depth. In any directed graph with sources from which all the edges go out and sinks into which all the edges go, the depth of the graph is simply the length of the path, the number of edges, on the longest path from source to sink. So for example, in this graph to the left, this is the source, this is the sink. There's a path of length 1. There's also a path of length 2. The longest path is length 2. So the depth of this graph is 2. Over here, again, this is the source, this is the sink. There's a path of length 1, there's a path of length 2. There is also a path of length 3. So this graph has a depth of 3. So when we apply the same principles in defining neural networks, we get the definition of the depth of a neural network. The computation in a neural network is usually directed. It goes from the input straight to the output. And the depth of the network is the length of the longest path from the input to the output. So here, for example, the paths from the input to the output go through 1 step, 2 steps, and 3 steps. So the depth of this network is 3. Now, can anybody tell me, here each block represents a layer of a set of neurons. Can anybody tell me what the depth of this network on the top is? Anyone? Answers, TAs, are there any answers?
You're saying 2. Most people are saying.
Perfect. So what about this guy here? What is the depth of this one?
4.
4, because the longest path is 4, right? Now, again, we kept speaking of layers. So what is the notion of a layer? What is a layer in a network? When you look at this figure, it's obvious what the layers are. When you look at this figure, maybe not, right? A layer is the set of neurons that all have the same depth from the input. So in this figure, for instance, can anybody tell me what the depth of this network is? Anyone?
Is 3? 4.
3, 4,
Also
right?
4's in chat.
So 1, 2, 3, 4, right? But then the set of neurons which are all at a depth of 1 with respect to the inputs are these red neurons. So these red neurons are the first layer. The set of neurons which are all at a depth of 2 are these green neurons. So these green neurons actually form the second layer. Visually, this green neuron doesn't look like the second layer. It looks like the third layer, right? But this is actually part of the second layer. The only neurons which are part of the third layer are these 2 yellow neurons, because they are at a depth of 3 with respect to the input. And the blue neurons are at a depth of 4. So you get the idea of depth. Now, moving on. So when I speak of a deep neural network, a deep neural network is a neural network that has a depth greater than 2. So it must have at least one hidden layer and an output layer, or it must have at least 2 hidden layers and an output layer. Then it's a deep neural network. So moving on, here's how we defined our multi-layer perceptron. It's a network of perceptrons, which I'll generally also call neurons sometimes, so don't get confused. After all, we're talking about neural networks. So these nodes.
I think there's a question from a student. They're asking, are there any benefits to non-typical designs like this?
Yes, lots, right? I mean, you're going to encounter many of these in the literature and even in the homeworks. So again, there's nothing atypical about this. This is just a layered network. I just drew it differently. The point was there's a very formal definition of what a layer is. And simply because I draw the network differently doesn't change the layer. That is the point, right? So here's the network again. It takes in some input and it produces some output. So the overall network is in fact just a function that embodies some input-output relationship. The question now is, what kind of input-output relationships can the network model? What kind of functions can it compute? Now, we've already seen that the network can compute Boolean functions operating on, we've already seen the network can compute Boolean functions operating on Boolean inputs and producing Boolean outputs, like this network to the left, which is a function of Boolean variables. And we saw that when you construct it properly, you can construct a whole lot of very complicated Boolean functions. We also saw that the MLP can compute real valued functions, like take in real values and output real values. For instance, we saw in the last class how to construct a network that approximately computes this blue function shown by the blue curve. The real question then is, what are the limitations? What kinds of functions can the network compute? Can we always construct a network to compute any function? Or are there limitations on what kinds of functions we can model with a network? And if so, what are they? And that is the topic of the rest of today's lecture. We will see that multi-layer perceptrons are universal Boolean functions. What I mean by universal Boolean function is you give me a Boolean function and I can construct an MLP that computes it. And in this context, we will discuss why depth is necessary for the network. We will also see that MLPs are universal classifiers. Give me any arbitrary decision boundary, and I can construct an MLP that captures it arbitrarily accurately. And again, we will discuss the need for networks to be deep. And finally, we will see that MLPs are universal approximators. Give me any input-output relationship, and I can construct an MLP that approximates it to arbitrary precision. And again, we'll discuss the issue of depth. In this context, we'll discuss the issue of the optimal depth and width of the network. And then I have this bullet here. This is historical. We have slides on RBF networks in this deck. I will not get time to get there. So let's start with the first topic, MLPs as universal Boolean functions. We know MLPs can model Boolean functions, but how well do they do it? Now, we know that individual perceptrons can model Boolean gates. We saw these figures in the last class. Again, the number within the circle is the threshold. The total input must match the threshold for the perceptron to fire. The numbers above the arrows are the weights. And so we saw that this arrangement of the perceptrons gives you an AND. Unless both inputs are 1, the threshold is not met and it will not fire. This is a NOT gate. It inverts the input. This is an OR gate. If either of the inputs is 1, the threshold is met and the unit will fire. But then the perceptrons can do a lot more than these very simple gates. This perceptron to the left is in fact what I call a universal AND gate. It's an input over it's a perceptron over n inputs. And this particular perceptron will only fire if the first L inputs are all 1 and the remaining inputs are all 0. Any other combination of inputs will not result in a firing. Let's see why. So let's first set it where to the situation where where you actually have just the target pattern. So if I have 1s over here for L times and 0s over here for the remaining n minus L times, then since these have weights 1, the total sum is L. What goes from here doesn't matter. And so under this specific condition, the threshold is met and it will fire. But then because these weights are -1, if I switch any of these to 1, this is going to become, the sum is going to become L minus 1, and that will not meet the threshold and it will not fire. Similarly, if any one of these becomes 0, then once again, this is no longer going to contribute to the sum. And once again, the sum is going to become less than L. And so this will not fire. And so you can see why you can set up the perceptron to fire under very specific conditions. This is a universal AND gate which can fire under very specific patterns of inputs. You can also have, and then you have this one here. This is what I call a generalized, this is a universal OR gate. This will fire if any of the first L inputs are 1 or any of the remaining inputs are 0. And so again, it's a complex function, and you can see why this is the case, right? So let's look at this guy again. Here, let's look at the one condition under which it will not fire. The one condition under which it will not fire is if all of the first L inputs are 0 and all of the remaining n minus L inputs are 1. So what is the total input coming in over here? These guys don't matter because they're 0. These guys, I have n minus L of these, and each of them has a weight of -1. So the total input that comes in is L minus n. If any one of these flips, then the total input is going to become L minus n plus 1, and it will fire. So this one is a universal OR gate, which is going to fire if any of these guys is 1, or if any of these guys is 0. So the perceptron is actually a fairly powerful little unit. Or here is a generalized majority gate. This will fire if at least k inputs are 1. You can see why. All of them have weight 1. If at least k of these guys are 1, the total input coming in is going to be k, and this will fire. So this is a generalized majority gate because now we can use this to count if the majority of inputs are 1. Now, if you want to construct the same Boolean logic using simple and simple Boolean gates rather than threshold units, you will need an exponentially sized circuit to compose this majority gate, but you can do it with a single perceptron. And so this is why Rosenblatt got fooled into believing the perceptron can compute any Boolean logic, because you can see, as you see, it can compute all kinds of very complicated Boolean functions. And yet, in spite of all of its versatility, the perceptron cannot model the simple XOR function. There's no combination of weights and threshold with which it will compute an XOR. To compute an XOR, you need to network multiple of these perceptrons. You will need a multi-layer perceptron. So this, for example, we saw is the network that computes the XOR. It has 3 perceptrons, 2 in the first layer, which we call the hidden layer because you don't really see their outputs. This first guy computes X or Y. This computes not X or not Y. The second layer, which is the output layer, consists of 1 perceptron, which just ANDs the outputs of the first 2 guys, and you get X, X or Y. In fact, you even have a, that's not the only way to build an MLP to compute an XOR. Here's a more compact way that I got from Gerald Friedland from Berkeley. This uses only 2 perceptrons, but now the weights are not all 1, and the thresholds are also not 1. So I'll let you figure out how this works. The thresholds are not integers. The upshot of this is that we've realized that we can compute Boolean gates using perceptrons, and in fact we can compute Boolean functions. And because you can compute any Boolean gate, it means you can compute any Boolean function, like this weird one over here, which computes a function of 4 inputs. So MLPs are in fact universal Boolean functions. Regardless of what Boolean function you give me, I can always construct an MLP that computes it. So MLPs are Boolean functions. They can be constructed to compute any Boolean function over any number of inputs and any number of outputs. But how complex will the network get? So in this network here to the left, for example, we saw that in order to compute this function, we have used 7 neurons in 3 layers. So the MLP that computes this function has 2 hidden layers. It's a deep network. If I had a more complex function of a larger number of inputs, how many layers would my MLP need to have to compute it? How does the depth of the network relate to the complexity of the Boolean function that it computes?
So there's also a student question. Someone's asking, is there an algorithm to generate the simplest equivalent perceptron?
Not really. It turns out that's an NP-hard problem. And you'll see in a bit why, right? So to understand how to construct this circuit, let's first consider this. What is a Boolean function? A Boolean function is just a truth table. I can list all of the inputs and the output, and I can make a table where for every combination of inputs, I list the output. And in fact, I don't have to do this for every combination. It's sufficient for me to just list the combinations for which the output is 1. For the rest of them, the output is implicitly 0. And so now we can write the entire function out in this form. Once you write it in this manner, you can write the Boolean function as a DNF formula, a formula in disjunctive normal form. The DNF form has clauses. Each of these clauses represents one combination of inputs for which the output is 1. So in each clause, a not x means that that corresponding x must take the value 0. So in this first clause, we are saying that x1 must take the value 0, x2 must take the value 0, x3 must take the value 1, x4 must take the value 1, and x5 must take the value 0. And under this condition, the output is 1. So this is not x1, x2, not x3, x4, x5. This third one is not x1, x2, x3, not x4, not x5. And so you have one such clause for every one of the 1 rows in the table. If the input matches any of these clauses, that clause is going to give you a 1. The summation is basically just an OR, so the overall output is 1. And no other input combination is actually going to result in this formula giving you a 1. So this formula exactly encapsulates this table. Now we can build an MLP for this formula using perceptrons that model AND and OR gates. We will have one perceptron for the first clause, one for the second clause, one for the third clause, one for the fourth clause, one for the fifth clause, and then one for the sixth clause. And finally, we will have one perceptron that ORs the output of all of these 6 clauses. And now you have an MLP that computes exactly this Boolean formula. And now this means that now, because you can represent all Boolean functions as truth tables, you can model any Boolean function in this manner. Note that this network has only one hidden layer where each neuron computes exactly one of these clauses in the DNF formula. This means that any Boolean function can be modeled by a multi-layer perceptron that has only one hidden layer. In other words, a one hidden layer MLP is a universal Boolean function. But then, if I do decide to just construct it using only one hidden layer, how large will the MLP get? How many neurons will I require in this one hidden layer to represent an arbitrary function of n variables? In other words, how large is this DNF formula going to get? So to answer this question, I am going to look at the truth table in a slightly different way. I'm going to look at it in the form of a Karnaugh map. How many of you are familiar with Karnaugh maps? Just raise your hands. So we have 204 people in class. I want to see how many of them know what a Karnaugh map is. A very small number. So a Karnaugh map is just a topological way of representing bit patterns. And it's topological because it means that bit patterns represented by adjacent cells only differ by 1 bit. So here, for example, is a Karnaugh map over 4 variables, w, x, y, and z. The 4 rows represent all combinations of w and x, and observe that any 2 adjacent rows differ in only 1 bit. And the bottom row is actually a neighbor of the top row, because those 2 also only differ in 1 bit. So this is actually a cylinder which is rolled over. So also each of the columns represents one combination of y and z. And again, the columns differ in only 1 bit. Adjacent columns differ in only 1 bit, and this last column is a neighbor of this first column. So this entire sheet that I've shown you is actually a torus. It looks like a donut. And each box over here now represents one combination of bits. So this box is the combination 0, 1, 1, 1 for w, x, y, and z. And so when I represent the truth table in this manner, the 16 boxes represent the 16 possible combinations of the 4 variables. And the highlighted boxes represent the input combinations for which the output is 1. So for this function, there are 7 highlighted boxes. So a very simple naive DNF formula would have 7 clauses. And if you just built an MLP to mimic that DNF formula, it would have 7 neurons in the hidden layer. But then you can begin reducing things. For example, these 4 boxes over here show that they all produce an output of 1, which means that it doesn't matter what w and x, what the values of w and x are, the output is always going to be a 1 when yz is 0, 0. So this entire block can be represented by the clause not y, not z. So also these two boxes, these two neighboring boxes can be grouped. And when you group these, it's telling me that it doesn't matter what the value of z is. So long as w, x, and y are 0, 1, and 0, the function outputs a 1. So this ellipse represents the clause not w, x, not y, because z can be ignored. So also now I can group these two adjacent guys. And that tells me that the value of w doesn't matter. So it's not x, because in both of these guys, the value of x is 0. So it's not x, y, z. In fact, I can group these 4 guys to come up with an even simpler class. So a single hidden layer MLP that computes the Boolean function for this truth table would only have 3 neurons on the hidden layer, each of which computes one of these clauses. And so long as the entries in the truth table can be grouped, the DNF formula that expresses it can be made smaller and smaller, and the resulting one hidden layer network that computes this Boolean formula can also be small. But then we're interested in knowing how large the one Boolean layer MLP can get, the worst case. What arrangement of highlighted cells simply cannot be grouped together and reduced? Anybody want to answer? I've already shown you the answer. What sort of arrangement here could not be grouped?
It'll be like a chessboard.
It'll be like a chessboard, because when you have something of this kind, there's no way you can group neighbors. And so this means that I'm going to require one DNF clause for every single highlighted cell. And how many clauses would I need over here? Anyone? Someone want to answer this?
8.
8.
People are saying 8.
Yeah, because I have 8 blocks. So and so this pattern, if I represented it using a one hidden layer network, would have 8 neurons in the hidden layer. So here's a 3D version of the Karnaugh map in 6 variables. And again, this has the chessboard pattern. How many neurons would I require in the hidden layer or to represent this Boolean function? Anybody?
Chat saying 32.
That would be 32. And this can be generalized. If you have a Boolean function over n variables, and you construct a one hidden layer MLP to compose the corresponding Boolean formula, you will need 2 raised to n minus 1 neurons in the hidden layer. So the size of the network is exponential in the number of inputs. But then if I allowed multiple hidden layers instead of just one hidden, okay, yeah. The poll.
Right, we have 7 seconds left.
2 seconds, 1 second.
Yes. Guys, you gotta be a little quicker than this. The polls are 30 seconds. We'll time this. If this time is too short, I'll have to adjust it. Anyways, so here's my question for you guys. If I use more than one hidden layer, can anybody guess how many neurons I would actually require to model this function? Anyone? I'm guessing no guesses, right? These functions are just XORs. This is W XOR X XOR Y XOR Z. This is U XOR V XOR W XOR X XOR Y XOR Z. And we already know that we can compose a single XOR using an MLP with 3 perceptrons, or in fact, using Friedland's technique, an MLP with only 2 perceptrons. And so for this function, we can construct this the MLP for this function as a series of just 3 XORs. First, you compute the XOR of W and X. Then you XOR the output with Y. And then you XOR that output with Z. And each XOR is going to require 3 perceptrons. So this network only needs 9 perceptrons. This one, which is over 6 variables, this has 5 XORs. Each of these XORs will require 3 perceptrons. So this deep MLP will only require 15 perceptrons. Compare this to the same one hidden layer MLP, where we needed 32 neurons for just the hidden layer plus the one output. So you needed a total of 33 neurons. This is with 15 perceptrons. But then more generally over here, if I have n input variables and I compose the network in this manner, then I'm only going to require 3 times n minus 1 perceptrons because there are n minus 1 XORs. And if you compare what you get with a naive single hidden layer MLP with what you would need if you were doing this with a deep network, a single hidden layer MLP would require 2 raised to n minus 1 neurons in the hidden layer plus the output unit. So this is exponential in n. Whereas if I do this with depth, I just require 3 times n minus 1 perceptrons. It's linear in n. So depth reduces the required number of neurons exponentially. Moreover, these neurons for the XOR network can be arranged in just 2 log n layers. How? Here's how you do it. The XOR is associative. I can begin grouping these XORs anyhow. So I can first compute an XOR of the first 2 guys, then an XOR of the next 2 guys, then an XOR of the next 2 guys, and so on, and pair them up. Then I can XOR their outputs in pairs, and then I can XOR those outputs in pairs, and so on. And each time I XOR, the number of outputs is reduced in half. So the total depth of the network is going to be log base 2 of n layers of XORs. Each XOR layer requires 2 layers of neurons. So you need 2 times log n layers. So the total number of layers in this network is simply going to be 2 log n. And the total number of neurons is going to be 3 times n minus 1. So the thing to note here is that each pair of layers, which I've highlighted in the blue box, is producing a set of variables that must be further XORed downstream. So this means that the same rules about the size of the network apply from the output of any one of these layers. So if you terminate, say, the net after only a few layers, say k layers, then you're still going to need to compute an XOR of the outputs of these layers. And computing an XOR using a deep network, again, we saw will require a linear number of neurons, but if you make it shallow, the number of neurons is going to become exponentially sized. So this means that if you reduce the size of the depth below 2 log n, the number of neurons required to compute the function is still going to grow very rapidly as you make the network shallower and shallower. And for any fixed depth network, the number of neurons you require is still going to grow exponentially with the number of inputs if you keep the depth of the network fixed. Also, there's a minimum number of neurons you're going to require just to be able to compute the function. If you take away just 1 neuron from this minimum number, it means you cannot even compute the function at all. In fact, for an XOR, if the minimum number of neurons, if the architecture requires some specific set of neurons, if you remove just one of these neurons, that network is going to be incorrect in computing the XOR 50% of the time. It's basically going to be giving you random outputs. Now, it's not really the number of neurons in the network that governs network size. It's actually the number of connections, because the number of parameters in the network is a function of the number of weights, and in this example, that's 30. So this is the number that actually.
A student is asking, if XOR is the worst case, will the layer reduction property still hold? It might not hold the associative property, but in the case of any other Boolean function.
So we're looking at the worst case. You're going to, for other functions, you're going to get something between the regular, being able to model it with one layer and the worst case. But in general, if you can sort of go by this property that you can believe you never, when you begin modeling functions, when you begin training networks, you don't know what the underlying function is. So assuming some kind of a worst case is the safe thing to be doing. Now, again, it's not really the number of neurons in the network that governs the network size, it's the number of connections. So here, for example, we have 30 connections. That's the number that really matters in software or hardware implementations, but doesn't really matter. As far as we are concerned, for our intuitions, we can continue to think in terms of the number of neurons, because a network that requires an exponential number of neurons will require an exponential number of weights. And so, to recap, deep Boolean MLPs that scale linearly in size with the number of inputs can become exponentially large if they're recast using only one hidden layer. And it gets worse. If you have any function, this is to answer the previous question, if you have any function that can eventually be expressed as an XOR, yes.
Poll is open.
The poll's open, guys.
Like 5
I'll
seconds
give you a
left.
few extra seconds if we can.
Okay, and then
Okay.
like,
Okay, stop here. So the answer is both 27 and 18 are correct answers. This is what you would get if you use 3 neurons to compute the XOR. 18 is what you'd need if you use 2 neurons to compute the XOR. Anyway, going back to our problem, if you have any function that can eventually be expressed as an XOR of some intermediate variables, like this illustration here, from that point on, you will need depth. And if you have a fixed depth from that point on, the network size can grow exponentially. So to summarize, an MLP is a universal Boolean function, but it can represent a given function only if it's sufficiently wide, it's sufficiently deep, and depth can sometimes be traded off for exponential growth of the width of the network. And optimal width and depth. So optimal width and depth depend on the number of variables and the complexity of the Boolean function. Complexity is the minimal number of terms in a DNF formula to represent it. And so the story so far, multi-layer perceptrons are universal Boolean machines. Even a network with a single hidden layer is a universal Boolean machine, but a single layer network may require an exponentially large number of perceptrons. Deeper networks may require far fewer neurons than shallower networks to express the same function, and that is why we need depth. Questions, anyone?
Professor, I have a question. So the XOR is the worst case for a Boolean function of n inputs, right?
Mm-hmm.
So if we have an architecture that is sufficient to represent an XOR, will that same architecture apply for any Boolean function which is intermediate?
It's not a universal architecture, right? For example, if I have a linear, you take a look at the slides. There's a theorem by Shannon, which shows that the vast majority of functions, by vast I mean super vast majority of functions, will always require an exponentially sized circuit. And he has a very nice, sieve proof for it. So take a look. But so what we are trying to do here is to give you an intuition. You can an XOR network cannot compute many functions. If I just give you this linear and n network that I had for XOR, there's a whole lot of functions that simply cannot be computed. The XOR is really representative of what happens in the worst case if you have too few layers. But then there are many functions that will require more than log n layers.
Thank you.
So to continue, we've seen how an MLP can operate as a Boolean function over real inputs already in the last class. We are going to revisit this depth, this topic today. Now, remember how the Boolean function, the MLP operates as a Boolean function over real inputs. A Boolean function effectively partitions the input space into regions, where in some region it outputs a 0, and in other regions it outputs a 1. So we have switched from talking about Boolean inputs to working on real inputs, but the output is still Boolean or categorical. And so by having different outputs in different regions of the space, you can actually get complex decision boundaries. We saw this in the last class. And to recap, a perceptron that uses this criterion to produce its output, where it produces an output if the weighted sum of inputs exceeds a threshold, has this kind of behavior. The boundary where the weighted sum exactly matches the threshold is going to be some sort of a hyperplane. And any inputs that lie on one side of the hyperplane are going to elicit an output of 1. For inputs on the other side, the output is going to be 0. So this is a linear classifier because the boundary between 1 and 0 is a hyperplane. That's linear. And if I plotted this using this extra axis to represent the output, so for two-dimensional inputs, x1 and x2 are the inputs, x3, and this vertical axis is the output y, the perceptron models this function, which is the step function, which is 0 until the boundary and then jumps up to 1. And now we also saw how the perceptron can model Boolean gates. For Boolean gates, the inputs are Boolean. So if I had a 2-input perceptron and the inputs were Boolean, then the inputs are either going to be 0, 0, 0, 1, 1, 0, or 1, 1. And now if the perceptron had this decision boundary, it's going to output a 1 for these 3 patterns. So this is giving you x or y. If this were the decision boundary with a 1 on this side, the perceptron is going to give you a not y. And now you can see why a single perceptron simply cannot compute an XOR. An XOR produces a 1 for the input patterns 1, 0 and 0, 1, but it outputs 0 for 0, 0 and 1, 1. So you want the output to be 0 till this line, then you want it to go up till the second line, and then you want it to go back down again. Whereas the perceptron can only model a single step function. So perceptron cannot model an XOR. Regardless, the perceptron can actually model fairly complex decision boundaries like the one here, where you want the output to be a 1 inside the pentagon and 0 outside. And we saw the way we do it is we'd have one perceptron for the lower edge of the pentagon, 1 for this edge, 1 for this edge, 1 for this edge, 1 for the 5th edge. And the only region in the space where all 5 perceptrons output a 1 is going to be within the pentagon. So if you summed the outputs of the 5 perceptrons, the sum is going to be a 5 only within the pentagon. Everywhere outside, it's going to be less than a 5. And now if I have a final AND gate, which applies a threshold of 5 to the sum, that is going to output a 1 only within this pentagon and 0 elsewhere. Now, observe that this network is not restricted to having pentagonal decision boundaries. I could also get a star-shaped decision boundary. Does anybody want to tell me how? Anyone? I can get a 5-pointed star.
Add in the 4s.
Pardon me?
Add in the 4.
How would you do that?
People are saying to use 4 as the threshold.
Yes, if you use the 4 as a threshold in this final neuron, then the actual decision boundary is going to be a 5-pointed star. Anyway, so once we know how to compose this pentagon, we can compose more complex decision boundaries, like this double pentagon, where, yes, this is an interesting one. A poll's open, guys.
Ten seconds.
Just give them a couple more seconds. They're coming in thick and fast.
Right. Gonna close it in 5 seconds.
So, yeah, it's true, right? Anyway, so if I want to compose this double pentagon, how do I do it? I have one subnet for the first pentagon, one for the second pentagon, and then I have this final neuron which ORs each of the outputs of each of these subnets, and now the total network is going to have an output of 1 if the input is in either of these pentagons. Observe that this network now has 3 layers. Using the same mechanism, now I can compose even more complex decision boundaries, like this crazy boundary here, or a decision boundary in the shape of a man, or in the shape of a horse, or anything else. For example, if I wanted this decision boundary, all I would have to do is to sort of split it up into many little polygons, have one little subnet for each of the polygons, and then OR their outputs, and I can construct this decision boundary. But now this circuit actually has 2 hidden layers. Can I do this using only one hidden layer? Or to be more explicit, suppose I want to construct this decision boundary, which is a double pentagon. How can I do it using just one hidden layer, a network of this kind? Does anybody want to take a guess? Any answers? Okay, I'll run out of time, so I'm going to show you how. Let's start with the simple diamond-shaped decision boundary. For a diamond-shaped decision boundary, I can have 4 neurons on the hidden layer, one hidden layer. And then when I sum their outputs, the output is going to be 4 inside the diamond, but it's going to be less than 4 outside. In these yellow regions, it's going to be 3, and the area of this yellow region is infinite. If I plotted it in 3D over here, for instance, this is the figure that shows the sum. And now if I use a threshold of 4, I'm going to get the diamond as my decision boundary. If I had a pentagon, then I'd have 5 neurons in the hidden layer. The sums of their outputs are going to be 5 within the pentagon. They're going to be 4 within the yellow regions. And the overall plot for the sum is going to look like this guy over here. Now, if I try to compose a hexagon, then the sum of the outputs is going to be 6 inside the hexagon. It's going to be 5 just outside, and then 4 or 3 in other places. If I wanted 16 sides, this is what I get. I have 16 within the 16-sided polygon, and then I have different regions of the space where the sum is less than 16. But then observe what's happening to the areas where the sum is less than 16 but greater than 8. And as I keep increasing the number of sides in the polygon, if I go up to 64 or if I go up to 1000, what we find is the area where the sum is less than 16 but greater than less than n for an n-sided polygon and greater than n over 2 keeps going down. So eventually, this is what I get with 1000 sides. When as I keep increasing the number of sides for the polygon, you eventually get to a situation where the area within which the sum is greater than n over 2 is always finite, and in the limit as n becomes very large, the sum of the outputs of these first layer polygons begins to take this shape, which is
Professor, students are asking how to interpret the axes on these graphs.
so the axes, the x-axes, this is on two inputs. So the x-axes are x1 and x2. The y-axis is the sum of the outputs of the hidden layer neurons. So going back here, right? Look at this guy. This figure, if you look at the sum, it's a 4 only within the diamond. That's what you're looking at. It. The figure to the left is showing the top view. So here, the sum is 5 only within the pentagon. You're looking at the top view. And eventually I stop showing the view to the left. I'm only showing you the overall plot. Is that clear? Okay. So in the limit, what will happen is that when n becomes very large, for a small radius, this sum eventually ends up becoming something that's arbitrarily close to a perfect cylinder. So roughly speaking, if I have a very large n, then the sum of the outputs of the first layer neurons is going to end up looking like this, with n inside this nearly circular, the sum being n inside this nearly circular region, and n over 2 outside. And if I just add in a bias which subtracts out n over 2, I'm going to get a sum of n over 2 within this region and 0 outside. But this is only true for very large n. And now, if I compose two networks, one for which composes a cylinder at one point and another which composes a cylinder at another point, and I simply directly sum their outputs. So this portion of the network composes this cylinder, this portion of the network composes this cylinder. What will the total sum look like? The total sum is going to look like the sum of this cylinder and this plot and this plot. And because the sum is 0 outside of these cylinders, the total sum is going to look like this guy here with a double cylinder, where the sum is n over 2 inside either of these cylinders and 0 outside. And now if I apply a threshold of n over 2, I get this decision region, which is two disconnected circles within which the output is 1 and the output is 0 everywhere else. And now when I know how to build this two disconnected circle decision region, with just, again, observe that this decision region has been composed now using just one hidden layer and a single output neuron, which compares the sum of these outputs to the threshold n over 2. And now I can keep adding more and more circles. And so if I want to approximate this double polygon, what I would need to do is to just fill in an arbitrary number of circles where more accurate approximations are obtained with a greater number of circles. And I can achieve arbitrary precision by increasing the number of circles and reducing their diameter. And so what this means is that that MLPs can not only capture any classification boundary, it means that even a one-layer MLP can model any classification boundary, which means that one hidden layer MLP, which means that regardless of the decision boundary you give me, I can construct an MLP with just one hidden layer. That one layer has to be one hidden layer that approximates that decision boundary to arbitrary precision. So MLPs, one hidden layer MLPs, are universal classifiers. But then here's where depth comes in. If I want to compose this decision boundary using just one hidden layer, I'm going to need infinite neurons on that hidden layer, and I'm still only going to sort of approximate this region. Whereas if I just added in a couple more layers, I got this decision region perfectly, and I got it using only 13 neurons. So deeper networks can require far, far fewer neurons. Now, there is, of course, a lot of formal analysis on the topic of optimal size and depth of networks, which view these as some categories of arithmetic circuits. I'm not actually going over the formal theory of it. Hopefully, the pictures that we saw convey the idea fully that the pictures are perfectly valid. So now, we get the idea of why even a one hidden layer network can construct any decision boundary. But then let's take a look at somewhat more generic patterns and look at some worst case functions. And again, I'm going to continue assuming threshold activation networks. This generalizes to other nets. Consider this decision boundary. The network must output a 1 within the yellow regions and 0 outside. If I try to build this using just a one hidden layer network, a naive one hidden layer network is clearly going to require infinite hidden neurons. But if I do this using 2 hidden layers, I need only 56 neurons. Why is that the case? That's because this decision boundary that you see over here is composed of 16 lines, which are shown in this figure to the top left. So each of these lines can be captured by one perceptron in the first layer. So you will need 16 perceptrons in the first hidden layer. And then there are 40 of these yellow regions, and these yellow regions are composed from the outputs of these line detectors. So I would need 40 neurons in the second region, second layer, and of course the final hidden final output neuron. So the entire network requires 57 total neurons. Now, but then this network is just an XOR of the outputs of these line detectors. You recognize this pattern. This is if my 16 line detectors output the variables y1 through y16. This is just y1 XOR y2 all the way until y16. So if I compose this using an XOR network, I just need the 16 line detectors, and then on top of that, now there are just 15 XORs, and I can do this with 15 XORs, which can be done using 30 neurons. If you use Friedland's model. And so this entire network can be computed using just 46. This decision boundary on 2 inputs can be computed using 46 neurons. Now, the gain from modeling this as an XOR doesn't seem like a lot because you went from 57 to 46. But then if you take something more complex, like this guy, again, a naive network with one hidden layer requires infinite neurons, but then this is composed of 64 lines over here. So you would need 64 basic detectors in the first hidden layer. There are 544 of these yellow regions, so you would need 544 neurons in the second layer. And so including the output layer, you're going to require 64 plus 544 plus 1, which is a 609 total neurons. But once again, this is just an XOR over these 64 lines. And so if I use 3 neurons per XOR, I can do this using 253 neurons. If I use 2 neurons per XOR, then I can do this using just 190 neurons as opposed to 651. Now, this is in 2-dimensional space. It's a very simple pattern in reality. As the patterns become more complex, the shallower network, the size of the shallower network for this pattern will increase rapidly, exponentially fast, as compared to the deeper network. Like in this case, this would be the XOR network. So, in summary, the number of neurons required by a shallow network is potentially exponential in the dimensionality of the input, or more correctly, in the number of statistically independent features in the input. And whereas if you do this with a deep network, you can require far, far, far fewer neurons, which is why you need depth. And so the story so far, multi-layer perceptrons are universal Boolean machines. They are universal classification functions. But a single hidden layer network may require an exponentially large number of perceptrons compared to the deeper networks, which means that deeper networks can be exponentially smaller than shallow networks. Deeper networks are more expressive. We've seen MLPs as Boolean functions, as universal classifiers. What about as approximators? By approximators, I mean when the output itself is neither Boolean nor categorical, but now must be real. We already saw how an MLP with 2 perceptrons can compute this little pulse where the input is 0. If I have 2 perceptrons with thresholds T1 and T2 and I add their outputs, then the input is going to be 0 until T1. It's going to be 1 between T1 and T2, and then a 0 outside. So if I have a threshold of 1 over here, I'm going to get this boundary, right? And then we saw subsequently that I can compose any scalar function of any scalar input with a one hidden layer MLP by simply approximating the function as the sum of many such pulses which are scaled to the right height. Now this is true for a scalar input, one-dimensional input, but this also generalizes to higher dimensions. It just gets a bit trickier. Now recall that a one hidden layer MLP can compose this cylinder or this hypercylinder in any n-dimensional space, right? In any high dimensional space, and this cylinder has a height n/2 within the cylinder and 0 outside. Or if you normalize it, it has a height 1 here and a 0 outside. And so to compute any arbitrary buff function with any arbitrary shape, you can approximate it by simply filling in the space with scaled and shifted with cylinders, and then with shifted cylinders, and scaling the different cylinders to the right height so that it approximates the surface that you want. So this means that even with just one hidden layer, a one hidden layer MLP is a universal function approximator. And so we've touched on these topics. We've seen why MLPs are universal Boolean functions. Let's take this poll. Yeah, poll, guys.
Any worded function can be modeled exactly by one hidden layer.
Okay, so the guys who answered false got it right, because it's an approximator. It cannot model these things exactly. It can approximate it to arbitrary precision, but eventually there will always be infinitesimal error in the worst case. So it's the neural network is a universal approximator. It's not a universal function. A one hidden layer MLP is a universal approximator. It's not a universal function. In general, neural networks are universal approximators, not universal functions. But approximation is good enough for our purposes. So continuing on the final bit, we're going to talk about the issue of depth. We've seen that a single hidden layer MLP is a universal approximator, can approximate any function to arbitrary precision. But having deeper networks helps. Now, more generally, deeper networks will require far fewer neurons than the shallow networks for the same approximation error. So the network is a generic principle, and the same principles that apply for Boolean networks apply over here. But then there's the issue of sufficiency. What are the limitations? So the neural network can only represent any function provided it has sufficient capacity to represent it. For example, for the given depth of network, even regardless of the depth, there is going to be a limitation on even the width. And if it does not have the sufficient width, then the network cannot represent the function. For example, consider this classification boundary. We need a net to produce 1 in the yellow regions and 0 in the gray regions. And the perceptrons have threshold activations. Keep this in mind, threshold activations. Now this pattern is composed using 16 lines. So a network with 16 or more neurons in the first layer is capable of representing this decision pattern perfectly. But then, if the network has less than 16 neurons in the first layer, say only 8 neurons, it cannot represent this pattern exactly. Why? So let's say these 8 neurons capture these 8 lines shown in red. Then the output of the first layer is only going to tell you, because the outputs are Boolean, right? I'm using threshold activations. So for any input in this region, or the output is going to be the output pattern is going to be the same. Any input within this red region, the output pattern is going to be the same. So the output of the first layer of neurons will not tell you, will tell you which of these stripes the input is in, but we will not tell you where you are within the stripe. So this means that if you have only 8 neurons in the hidden layer, I don't care how many neurons you put in subsequently. I don't care if you put infinite layers of infinite depth after the first layer, you are not going to capture this decision boundary. Even if the 8 neurons capture these 8 lines, the only information you're going to have is which of these grid cells you're in. And adding any number of neurons after this layer is not going to recover enough information to model the function fully. So even if you have the full complement of 16 neurons in the first layer, if the second layer has less than 40 neurons, there are 40 distinct yellow regions. If the second layer has less than 40 neurons, I don't care how many more layers you add after that second layer, you are not going to capture this decision boundary. And so this means that you're going to have, or there are caveats over here. Remember the XOR network. But the point here is that it's even if you have the freedom to increase the depth of your network arbitrarily, there may be restrictions on the width. And if you go below the minimal width, the pattern, the function that you're trying to model may not be modelable. The pattern you're trying to detect may not be recoverable. But there's a caveat here. And what is the caveat? In all of our explanations, we used a threshold activation, which gates information. So when the input is on one side of the threshold, the output is 0. On the other side, it's 1. So because of the threshold activation, here, for example, if I had only 4 neurons, I'd only get this level of information at the output of these 4 neurons. I'd only know which stripe I'm in, on which side of each of the lines the input lies, but it won't tell you how far you are from the line. And so the subsequent layers in the network do not have sufficient information to partition the space as needed. If, on the other hand, you used a continuous activation function like the sigmoid, the sigmoid produces graded output. So the output of the sigmoid would look something like this. Rather than just red and yellow, it's going to sort of grade out. And so the output of the first layer of the network is going to be something like this, which means that you still have information.
This meeting is being recorded.
What happened? Wait, did the recording just stop?
No, someone had his mic on. I think when you get disconnected and you come back, you get that notice.
I see. So when I use this graded activation function, then I'm going to get information about how far you are from the boundary. And so subsequent layers over here can add information about, can add additional boundaries in this direction at least. So you having information about how far you are from the boundary means that you can potentially get away with having fewer neurons in the earlier layers. But then even there you have some restrictions. So for example, a sigmoid quickly saturates, so it tells you how far you are from the boundary only for a little while, and then after that, that information is lost. If you have something like a rectified linear unit, then on one side of the boundary, it continues to tell you how far you are from the boundary for a very long time. So this guy is clearly better than the sigmoid. And ideally, you would like to have that information on both sides of the boundary. And so something like this leaky reloos, which you will encounter in class, which basically change behavior at the boundary, but tell you how far you are from the boundary on either side, are going to be more effective still. So, narrow layers can pass sufficient information to subsequent layers if the activation function is sufficiently graded, but will require greater depth to permit later layers to capture patterns. Now, all along, we've been speaking of yes, this is the last poll, and we have 1 more minute of class after the poll.
We might need a little bit more time for this one.
Yeah, we'll give them a little more time. The lecture is done. I'll just need about 30 seconds after this.
Also, Professor, a student was asking on slide 133 why they needed 40 neurons in the second layer.
Because there are 40 yellow boxes. So remember, it's an XOR, right? If I just add 1 more layer, then I need 40 of those. Again, it's an XOR. I could do this by pairing things up. But if I had 1 more layer, I needed 40.
I'm gonna close the poll soon.
All right, guys, let's stop this here. And we'll discuss this question on the answer, right? So just in closing, we've been speaking of the capacity of the network, and there are in fact very many definitions, formal definitions of the capacity of a network, like information or storage capacity or VC dimension, and various other issues. We'll have a guest lecture by Gerald Friedland who will talk about this in greater detail, so I'll skip this. And so the lessons for today, MLPs are, again, final thing. So again, if you want to model a function, we need to have a function of a network of sufficient capacity, which means sufficient width, sufficient depth, and the appropriate activation function. So the lesson that we have is for today, our MLPs are universal Boolean functions, universal classifiers, and universal function approximators. Even a single hidden layer MLPs, all of these deeper MLPs can achieve the same precision of approximation with far fewer neurons, so they are more expressive, but more graded activation functions also result in more expressive networks. And so the capacity of your network is going to be a function of the number of layers, the width of, so the function of the depth, the width of each layer, and also the activation function, specific activation function that you use. And regardless of the choice, if there's a limit on the size of the network, there's always a limit on the complexity of the function that it can model. And there are some functions that it can simply not model with an error of more than 50% or so. So we'll stop right here. I'll stay online for a minute more for questions, but thank you. Questions, anyone?
Professor?
Yeah.
If more graded activation functions are more expressive, what's stopping you from just doing like a one-to-one function, like f of x equals x?
So the real magic in the neural network lies in the nonlinearity. If f of x is x, then things collapse. A million-layer network is no different from a one-layer network, because a sequential chaining of many linear transforms is just one linear transform.
Okay, thank you.
So linearity, non-linearity is critical. Anything else?
Yeah, I had one quick question on the 18 versus 27. So I didn't really quite understand how you can make a XOR with 2 neurons.
So this was there was a slide way up early, which I asked you to take a look at. In fact, download the slides and take a look. Gerald Friedland gave us a circuit that computes XORs with only 2 neurons. I mentioned this early in the class.
Okay, thank you.
Okay, guys, thank you. Thank you, everybody. Stopping the sharing and terminating the meeting.